Thank you for the opportunity to talk today. I look forward to presenting what we've been working on. It's going to be a little different. This is my first time to this conference, and there's really a lot of focus here on drug discovery, and I'm going to talk to you about clinical decision making. I want to introduce Sheena Kerr, who's in the audience here, and she'll be giving a talk tomorrow, actually, on a subset of this. But she's really led this work. She's a research assistant professor in the lab. And then the other partner in crime here is Josh Lang, an oncologist, physician scientist who we work with closely on a number of projects. So our goal really is to see if we can help the clinician make decisions in the clinic. You'll see by the end of my talk sort of where we're at in that journey, which is really about a 10-year journey now. So what I want to talk to you today about, first I want to set up that clinical environment and that clinical decision making and actually show you a patient to make this a bit more personal, and then show you the types of models we're developing, and then talk about a very specific project that's funded by NIH under their Clinical Trials on a Chip program to look at prostate cancer, specifically bone metastasis in prostate cancer. So for those of you not familiar with oncology and cancer treatment, 25, 30 years ago, it really didn't matter if you knew anything about the person's cancer, because there was basically only one treatment, chemotherapy, maybe radiation. So the physician didn't really need any tools because they wouldn't have any choices to make. But over the last 10 or 15 years, there's really been an explosion of the number of therapeutics now available, both small molecule originally, but now all of the biologics and immunotherapies. Unfortunately, the clinician still is left with very little information to make those decisions, and we're actually integrated into the clinical system at Wisconsin. So over the last 10 years, we've really gotten to see and work with clinicians regularly and hear these anecdotal stories, and they really don't have much information, and often they're really flipping a coin, with a few exceptions. They really don't know which drug to give which patient, and the goal, of course, would be to be able to make sure you got the right treatment for each patient. Even it's also very useful to be able to know that there's no drug that's going to work, because then you don't waste the patient's time and the system's money and their emotional stress of going through a treatment that isn't going to work. That's equally as important, but we're nowhere near there now. Now with cancer, this is a really challenging problem, because as a scientist, when I first got into cancer mid-career about 15, 20 years ago, it's amazing. It's an amazingly interesting disease to study from a pure science perspective, because it's so complex, it's changing and evolving real time. Unfortunately, that makes it really hard to study and to be able to predict, because each patient's cancer is unique. In fact, within a given patient, the biology of a metastatic site might be quite different than the primary site. Even within a solid tumor, and we've done some of this work, you can find different biology depending on where you probe a single tumor mass. And it's changing over time, continually, in response to a first-line therapy, etc. So it's a really challenging issue, and just to put a face on that, here's an example of one of Josh's patients, a 57-year-old male with metastatic castrate-resistant prostate cancer. He presented with metastatic disease at age 53, was treated with a series of treatments, responded to some of them for a while, but ultimately always regressed. At some point then, they did a PSMA PET imaging and found lymph node involvement. They treated with a targeted radiotherapy, PSMA treatment. They saw a complete response to the lymph node. The lymph node disappeared, but now suddenly you have bone metastasis. So this is sort of an untenable situation, but this is a very typical situation. I also should say a lot of prostate cancer you don't die from, but those that metastasize, 75% of those that have metastatic disease go to the bone. And of those that have bone metastasis, the 5-year survival rate is only about 5%. So this is a significant subset of prostate cancer patients for which there's really no viable treatment today. So this is unsatisfying. Why the dramatic change in disease state? Really all along treatment, but particularly at this state. Why was the lymph node so sensitive to treatment, but then bone pops up? Does this new TME, this altered TME, drive resistance? And ultimately, how does the clinician decide what therapy to give this patient next? So the point here is that every patient is unique. It's dynamic over time. What order you give a treatment in affects the biology over the course of that treatment. And when you work with clinicians and surgeons, you actually hear anecdotal stories where, they sometimes give the patient a drug and it actually makes the cancer worse. So you'd like to avoid those situations as well. So the problem, of course, is that they're really working off of, a little bit of genetic, molecular information and imaging data, and that just doesn't answer these questions. And traditional preclinical models aren't well suited for this because they don't capture these complex microenvironments and they don't capture the dynamic response to treatment. So I'm going to take a little bit of an aside here, one slide aside, and step back 10 years to tell you sort of how we got started in this. And we had an R01 with Shigeki Miyamoto, who studies multiple myeloma basic cancer biology, and he and others had data that suggested that the stromal compartment influenced and regulated the response of patients to first-line therapy, in this case bortezomib. So at that time we weren't doing MPSs, we were just doing simple microfluidics, but when you do a bone marrow draw from a patient, you might only get 50,000 cancer cells. So this was a case where just shrinking the co-culture systems to a very small scale allowed us to do these experiments that couldn't have been done any other way. And we did very simple experiments where we monocultured just the cancer cells, and then we had this very simple microfluidic device that allowed us to co-culture all of the stromal cells, all of them. We didn't isolate them individually, just all one mixture with the cancer cells. And what we saw, and this is published, so I'm going to skip over it quickly, is what we saw is that without the stroma, we had no predictive value. With the stroma, in this small study of 17 patients, we had perfect 100% predictive value of which patient was going to respond to first-line therapy. So this is obviously very exciting, got published, and Jerome Pack, a graduate student and postdoc at the time, has started a company, well, about 6-7 years ago now, out in La Jolla, and they're advancing this towards a clinical companion diagnostic for multiple myeloma. So this is a hematological cancer, and so it's maybe not surprising that a simple system like this was able to replicate, because structure, you could argue, is not so important in a hematological cancer. But when you think about solid tumors, and for example, the immunotherapies don't work very well in solid tumors, clearly we need better models than this to understand solid tumor biology. But one point I wanted to make here, and I'll make it at the end as well, is that ultimately in the clinic, the simplest solution is going to work, right? We don't want to overcomplicate them if we don't have to. That said, we have now taken the opposite approach, and we've made the most complicated MPS, I think, to date that we know of, that includes 8 cell types. And so our approach is quite simple. We get tumor biopsies or resections from the patient. We isolate all the cells into their individual components, and I'll tell you more about that. And then we recapitulate the tumor vasculature and microenvironment. So we use a platform we call Luminex, which was published a long time ago, but I'll briefly describe, that allows us to mix and match these components, and ultimately in the most complex embodiment we build a lymphatic vessel, a blood vessel, a tumor spheroid, mimic, and then the stromal and immune cells. In the project I'm going to focus on today, there's an actual picture of one of the devices we use for this project, where we use iPS-derived endothelial cells to make the vessel, and then cells from the cancer patients to make all of the other compartments. So briefly, lumens are everywhere, and when I first started studying cancer, I realized if we're really going to study cancer, we can't ignore lumens, both from their involvement in the metastatic cascade, circulating tumor cells and vascularization of a tumor mass, but also in breast and prostate, for example, in the initiation stages of cancer often occur in a ductal structure. So we wanted to be able to make lumens. We've got a nice system for doing that now. But then the first question was again, do we need lumens? Does it make a difference? And it turns out it actually makes a big difference. So if you put, for example, epithelial cells into a luminal structure and compare them to just 2D culture, it dramatically changes their proliferation rates, and the proliferation rates actually become identical to in vivo. It increases when you put cells into a lumen versus 2D culture. It increases their sensitivity, in this case to toxins. Another advantage we found of actually building lumens is a very practical one, is pathologists and surgeons love to talk to us, and it's just a different conversation now because they can see the same endpoints in our models as they see in a pathology stain and microscopy. So it's really facilitated drawing in the clinical side as well. And then we've also done experiments to look at, again, what levels of complexity make a difference. And this is just an example of looking at response to an anti-EGF drug, where, in fact, if you co-culture, just do 2D co-culture, that changes the response, not surprisingly. And if you do a 3D mixed culture versus a spheroid, that changes. So the point, really, of this slide is that this community, and this is some of our data, but there's lots of other data in the literature that really suggests that in many cases, structure is really important. It changes the biology, and then the ultimate question is it actually better biology? So with that, I want to come back to Josh's patient. Because that's our target audience for this project, is this subset of prostate cancer patients that have a very poor prognosis. So in these patients, it's a very immune-rich bone microenvironment. It's highly vascularized. So now this is sort of this context of youth that was talked about in a couple of talks, where how we choose which components to put into these models is based on the treatments we're going to trying to be study, as well as the biology of the disease state that we're interested in. So in this model, then, we've chosen to include all of these cell types: fibroblasts, osteoblasts, adipocytes, bone marrow stromal cells, and osteoclasts, macrophages, and the spheroid and the endothelium. Okay, and I want to give you a sense of the effort that goes into this. And be realistic, because these are not easy to build nor high throughput by any stretch of the imagination. And I'll talk about that at the end in a little bit. So we start with bone marrow mesenchymal stem cells from cancer patients and blood draws from cancer patients. From those, we isolate the MSCs and the monocytes, and then we go through a differentiation process that takes up to 3 weeks to produce these different cell types, these different primary differentiated cell types. And we now sort of have this process ongoing in the lab all the time. Now we have all these cell types, we need a media that allows them all to be happy together. Sheena could spend a whole talk on this slide, because this was a big effort. It was facilitated by a very simple co-culture system that was recently launched, called the MicroDuo, which allows us to do very high throughput co-cultures by just adding more media to a two-chamber system that connects the wells. So using this system, we did a ton of experiments and ultimately came up with what we call a multi-phenotype media that's based on 3 base medias that are available plus 13 supplements. So it was a really significant effort to do this. We'll be publishing this and making it available for anybody who wants to use it. So now we have it all. Does it work, right? So we have it all. We have all the stromal cells and the endothelial cells. So now we did a bunch of characterization work, which will be published soon. And I'm going to sort of fly through this pretty quickly, but so the stromal cells are viable over time for up to 2 weeks, and in some cases we've taken them out further than that. The bone cells are actually doing what they're supposed to do, in this case mineralizing the matrix, and we see it increasing over time. So these cells are likely continuing to differentiate in these systems when you get them all together. All signs are good, and then a bunch of gene expression work as well to measure the phenotypic state of these cells, both from gene expression and functional. So I'm not showing you nearly all of the data here, but the point is we've now got this system where we can really create a fairly homeostatic system where these cells are all happy with each other and maintaining their phenotype over time. So now that we have that system, we still haven't done anything with the cancer cells. So the next step then is to think about the cancer cells. So we take the epithelial cells, isolate them from tissue, and then grow spheroids. So that's pretty standard, nothing new there. but just an example of spheroid viability and growth from a couple of different donors. Again, all looks nice. Now, the next question, now we're actually ready to start thinking about putting a drug on these systems. And the drug that I'm going to talk about today is sacituzumab govitecan, which is a antibody drug conjugate that targets a TROP2 antibody that's known to be upregulated in prostate cancer, and it links it to a cytotoxic payload. So this is a targeted therapy that's approved for some indications, but not yet for prostate cancer. So the first question is, can we put this drug into this model, and will it get out of the lumen, out of our blood vessel? So this is simple diffusion study where we put this labeled drug into the system and see if it diffuses out, or in many cases use a mimic molecule to do this. And we wanted, we've done this over a number of patients, and in fact the lumen seems to be pretty consistent and allow the drug to move out of the lumen. So keep in mind now, the nice thing about the system, we're actually able, instead of the whole process being a black box, we're actually able to monitor the whole process from injection of the blood into the bloodstream, its movement out of the vessel, and then its killing capacity and its effect on the cells in the microenvironment. So we now have the whole system up in the corner there. You can see the system that everything else is going to be based on. So we've got the matrix, we've got the tumor spheroid, all the stromal cells, immune cells, and then the blood vessel, in this case, made from iPS-derived endothelial cells. Also a comment that sort of came up in some other talks I've heard here, right? So we'd ultimately like to use everything from the patient, all cells from the patient, and it's just a practical decision. For example, we do some work in renal cancer where you actually get huge tissue masses that are highly vascularized. In those cases, we actually can isolate endothelial cells right from the tumor and use tumor endothelial cells. In a prostate, we get very small amounts of tissue. We aren't able to get enough endothelial cells to be able to use them, so we use an iPS drive. And I think that's just the practicality of this field. We're going to have to mix and match as available and try to get as close as we can to the patient. So again, a slide that represents an enormous amount of work that I certainly didn't appreciate or expect we were going to have to do this, but we get to make a long story short, we get a vial of the drug from Gilead, and it doesn't work. So we spend a number of months actually working through with Gilead all of the issues of shipping and thawing and freezing and ultimately what dose should we be putting on these models. Because these are not, though we call them MPSs, they're not physiological, right? We don't know, just because you give a patient a dose doesn't mean that's the dose that's going to work in this model. So in any case, we did a ton of experiments here and the punchline is that as you'll see, we ended up at choosing, this is how we chose the dose and the protocol for applying the drug to the model. So then we wanted to, because we ultimately are modeling patients, but again, we have limited cells for each patient. So first, we did these dose studies and testing with cell lines, right? So we wanted to have some confidence that the dose we had chosen is going to be reasonable. So we used 3 different prostate cancer cell lines that have known TROP expression of low, medium, and high TROP expression. I'm just showing one representative data set here from the medium TROP2, a DU145 cell line. And then to this just simple 2D killing assay, we apply isotype ADC, so that is non-targeted. So it's a non-targeted cytotoxic agent. The TROP2 ADC, which is the antibody-linked targeted drug, and then a positive docetaxel control. And you can see here in the isotype, when it's not targeted, if you go up enough in dose, so when you get up to 25 micrograms per mil, you start to see killing, non-specific killing, because you just have enough of this stuff around, starts killing cells. If you target it to TROP2, then the cell death, the cancer cell death, is more targeted, it's more effective, and you see at 5 micrograms we're starting to see significant effect. and then the positive control showing that everything's working correctly. So based on this, we sort of honed in on and many other experiments honed in on 5 micrograms per mil. Next question, all right, let's go to 3D. Does this dose still hold up in 3D? Not yet wanting to risk using our precious patient samples. So we again did this across the 3 different cell lines, but here we made spheroids and we actually put them into the MPS system without the stromal cells to keep it simple and because we didn't want to waste them, but with the endothelial lumen. So we are replicating the transport of the drug out of the blood vessel and to the cancer cells. And what you see here is I mean, we really didn't know exactly what to expect based on a lot of other work, whether, because what we've seen in the past, sometimes 2D is predictive of 3D, sometimes it's not. In this case, it was pretty predictive, right? So you see we see a response in the TROP2 medium and the TROP2 high. I just mentioned here at the bottom, I list the proliferation rate of these cells because you have to think about that as well. That influences the response. But we were pretty pleased with this. It confirmed that our 5 microgram per mil dose was in the right range and that it was getting out of the endothelium and into the cancer. So with that, then we went to the final stage of saying, does this actually work with patients, and can we see a differential response in these models that correlates with patient response? Or I shouldn't say patient response in this case, just differential, and in this case that correlates to a known TROP expression level in these patients. So we chose 3 donors that have 3 different levels of TROP2. So sort of replicating those cell lines that we had, but now with actually 3 distinct patients, one that had TROP2 low, one that had TROP2 medium, one had TROP2 high. And to bracket our risk, we also included a 10 microgram mil per dose here. And what you see is, if you look at the TROP2 low, so 5 microgram was not enough to see a differential killing there between the isotype and the targeted. When we went to 10, it was. If you go to the TROP2 medium, you start to see it at 5 micrograms, you see it more at 10, and with TROP2 high, you see it at 5 micrograms and also at 10. So this was very satisfying after really several years of work to bring this all up to speed. We've gotten to the point now where the whole system works. It's repeatable as much as we can tell at this stage, and we're now ready to move into clinical studies. So to give you a sense of what the whole process, again, because I don't want to sweep anything under the rug. These are really difficult studies to do, and they take a lot of time, right? You have to coordinate with, get all the approvals, get surgery, get the tissue samples. We're lucky in Wisconsin that we're in the same building as the hospital. We don't have to. It's very convenient for us to just run over to the surgical suite and get the samples. But then it's a couple weeks process to do all that digestion, all the confirmation from pathology, etc. Make the devices, which is fairly trivial compared to everything else. And then actually build the MPS, which I won't describe in detail here. You've sort of gotten the sense of all of the process to do that. And then apply the therapy. The nice thing about these is we really can apply any therapy to these systems. And as I mentioned, Shino tomorrow will be talking about a head and neck project where we're using these to predict radiation, response to radiation therapy. And then also the readouts. Obviously, we have a plethora of readouts that we can go after in these systems, both functional and traditional omic systems. So the status of the clinical trials on a chip project is that we've completed our what they call the UG3 phase. We've now been approved to go on to the UH3 phase, which will be clinical studies looking at a number of different experimental ADCs and seeing if we can stratify these patients. So we think, for better or worse, we've made perhaps the most complicated MPS to date with 8 unique cell types. Time will tell whether that's actually something to be proud of or not, because it's sort of the opposite approach that I've taken in many other things. We sort of went for the most complex, and then we'll back out later. the system works well. It actually sets up a nice homeostatic system that's quite stable over time in culture. Something I haven't mentioned and we haven't done yet, but I think we're going to actually do sequential treatments in these systems. We'll actually be able to do first line and then look at the development of resistance and apply second line. I think that's going to be really exciting in these systems. The optimization of this was painful and took a long time, and really hats off to the staff and students that accomplished this. And again, now we're ready to head into informing clinical care and seeing if this actually is predictive. With the good news that we have one case in multiple myeloma where we already have shown that we are predictive, and that's moving into commercialization. So hopefully these will follow. So the last thing I wanted to touch on before concluding is I've talked to you really hyper-focused on this, our primary goal of getting into the clinic. And to get into the clinic, right, you actually don't need to understand anything about the biology. If it's predictive, it's predictive. It actually doesn't even matter if it's causal or if it's the same mechanism. If it's predictive, and they'll use it. And I think that's a lesson I try to, particularly when I'm talking to sort of hardcore cancer biologists, right? Because they always feel like they have to understand mechanism. And no, we don't have to wait for mechanism necessarily to help patients. But as you can imagine, these systems, we hope, will be very useful for understanding mechanism and for discovery. So here's an example of a paper that just actually published, I think, in the last couple of weeks, that we used this system in head and neck. Ravi's a MD PhD student that did most of this work. In this case, to actually discover a new role for a lymphatically secreted, so this is a model that has the lymphatic vessel in it, for lymphatically secreted monocyte migration inhibitory factor, so a known factor, but this role had not been known before. And just briefly, we see a donor-specific response here. This is a case where we're really looking at the fibroblast component of the stroma and its effect on this. And you see with 3 different donors, we see 3 different levels of response. And then this new observation that, in fact, the upregulation of MIF is occurring in the lymphatic compartment. And I'll put in a plug for people to not forget about lymphatics. Again, when you talk to clinicians, that's all you hear about is lymphatics, but it's really understudied from the basic science perspective. So lastly, I just want to sort of tell you where we're at and where we're going. So we, thankfully and appreciatively to NIH, we have 3 funded projects now that all include clinical studies. The one that I described today, the one that Chino will describe tomorrow on head and neck, and then another one on a different aspect of prostate. We also just got an R01 to start applying these models to understanding the basic mechanism of parasitic infection in infectious disease. And Jose, a scientist who's now a tenure-track faculty at Wisconsin, is really focused on immunotherapy applications of these systems. And excitingly, we just started a collaboration to look at vessel inflammation with blood from sepsis patients in these systems as well. So finally, last slide, I want to just sum up and say the way I think about these models, at least that we're building, and I think it applies to a lot of MPS, particularly when you're working with primary cells, is that it really sort of muddies the water between what we call in vitro and ex vivo. So traditionally, tissue and blood samples didn't really make it into the research realm, right? They just went to the clinic, to the pathology, and were used for clinical treatment. But now, because of this, really because of the small scale, we can take these precious samples and we can actually build a bunch of things with them. So we can port them over into the in vitro models that used to be reserved for mechanistic studies and actually feed that back into patient stratification in a clinical setting. So I think it's exciting. I think I have a hard time imagining this system actually being adopted in the clinic because it's so time-consuming, and my hope is that with these systems we'll discover simpler biomarkers that can actually be used clinically and help Josh's patients and others. And with that, I will stop, thank NIH and all the folks that worked on this, and maybe have time for a question or two.
Thank you very much, David. Wow. Okay, one question I think we can.
Thank you very much, David, for sharing. Estrela Neto, I3S Portugal. I understand that the bone metastatic niche is a very messy microenvironment, but besides the percentage of the cellular populations, were you concerned with having some structured positioning of the cells? And also, I missed the time frame of your study. At some point, do you have overpopulation of the cancer cells in your system? Thank you.
Yep, so there's sort of two questions there, and I'll answer them quickly. So we don't see overpopulation. When you put enough cells together, they actually are quite happy, and as I mentioned, they actually slow down their proliferation. So we don't see that problem. And I'm sorry, now I forgot the other question. Oh, the structure, yeah. So importantly, so some structure is obvious. One thing that we're doing next now is we're actually doing RNA-seq on the patients so that we can match the percentage ratio of cells. So in the bone marrow, there's not a lot of structure, so I think we're not far off from in vivo there, but we are now taking that next step to actually be able to match the ratios of different cell types to the specific patient.
Okay, thank you, David. I think David is around if you have any more questions.